Hi, my name is Aman, and today I'll be presenting my project on exploring priors for inverse rendering. So the inverse rendering problem deals with a single RGB image where we would like to estimate its normals, albedo, shading, and environment map altogether from just the single image. This is inherently ill-posed because there can be an infinite number of such factorizations that result in this image. However, in the real world, only a few of these are likely to occur. And in this project, I look at ways in which we can harness this knowledge to generate realistic factorizations of the image. So I look at this, I use priors from this paper by John Barron and Jitendra Malik, and primarily focus on three categories of natural priors: priors on illumination, priors on albedo, and priors on shading. So the first one is prior on albedo, and this essentially arises from the observation that natural images are generally smooth. So what I've done here is learned a Gaussian mixture model over the differences in the log albedo. Um, this is a heavy-tailed function. As you can see here, this is the learned Gaussian mixture model, and it peaks at a difference of 0, which is to say that in most cases there is no difference in adjacent albedo values. Um, Now, the reason why we learn this over the difference in log albedos is that um, using a difference in the log space effectively cancels out differences due to scaling and makes this whole optimization process scale invariant, while operating in the log space also prevents the need of clipping albedo values at 0 and makes the overall optimization process easier. While this is nice in theory, I found that when I actually optimized it, it was not as easy. So here I have an image, and in the middle I have its PDF of the differences between its log albedo values, and you can see that this is also heavy-tailed. However, when you try to optimize this using the gradient of the negative log likelihood, I found that these gradient values were extremely large, and this prevented uh, the algorithm from learning a useful factorization of the image. This was not a one-off incident. This happened in other images such as this one as well, where you have the same heavy-tailed likelihood function, but extremely large gradient values which prevent learning. As a result, images often look like this, where the factorization of depth and shading were just noise and contained absolutely no meaningful information. Um, Subsequently, I looked at a second category of priors, which was priors on shape. So one of these priors is called the surface isotropy prior, which essentially states that it is equally likely for the surface to be oriented in either direction. However, most surfaces that we observe are oriented towards ourselves. As a result, we can bake this bias into our algorithm and maximize the value of the z coordinate or the unit surface normal. I found that while there were minor improvements, without a good smoothness prior on the albedo term, this did not really improve the quality of the factorization over what you are seeing over here. And as a result, this also failed to yield a good factorization of the input image. This image that you see here is just highlighting which regions maximally activate the surface isotropy prior. Those are specifically the regions in white, uh, which are oriented towards the camera. Finally, I looked at priors on illumination, and for this, I fitted a multivariate Gaussian over spherical harmonics designed to produce log shading. Under this model, you can see that from left to right are more to less likely environment maps. On the left is the most likely environment map, which contains soft shadows, lighting from the front, while on the right are hard shadows and lighting from side angles. So using this, I estimated illumination given an image and its depth map, and was able to get fairly realistic environment maps by just maximizing the likelihood under this prior. So you can see in this apple, the lighted region is well captured by the environment map, while the shadow region is also fairly faithfully covered. Um, yep, that's about it. Subsequent work, I would like to try and get the smoothness priors working, and also explore other priors that are dealt with in the paper, such as the sparsity priors and other priors on shapes.